1 plus 1 equals 2. Is this true? We never question this statement and just letting it go by without understanding it. I can even make scraps of symbols and declare that this is how we count from now. However, I'm not the supreme world leader who could change rules how I like it, and we are stuck to the system. So, what is this? It's a drawing of lines. We call it 1. According to Merriam-Webster, it's defined as being a single unit or thing, or the first whole number above 0. But 1 is just a mere substitution of the quantity of something or group. Any number is. We wrote compounds of stroke to replace amount of objects we observe, listen, or process, such as 1 apple, 2 people, 11 eggs. Number is also used to represent abstractions like temperature, mass, length. Whether we use measuring tools or not, we can save time by calculating the prediction close to the expected number. Many countries use their own symbols based on their culture and heritage. Here's a pair of scissors, which represents number 7. Crazy work. Therefore, we can conclude that each number has their own unique symbol. But why does 10 use 2 of them, 1 and 0? Let's talk about addition to cover this problem. Say we have an object. I'll take a cube. To get the cube, we must imply that 0 is a natural number and each number has a successor, which means a next number coming in. Those are the first and sixth definition of Peano axioms. Successor of 0 is 1. We can take this new number as the first variable of the recursion. We will step back to the original question, which is to prove 1 plus 1 is equal to 2. To get to number 2, we will use the second definition of addition recursion. A plus successor of B is equals to successor of A plus B. A is 1 and successor of B is 1. As B is the predecessor of 1, B must be 0. So, we can simplify the equation to be 1 plus successor of 0 is the successor of 1 plus 0. 1 plus 1 is equals to the successor of 1. So 1 plus 1 is equal to 2. According to the natural number line, successor of 1 is 2. This equation will work for any number. Here's 5 plus 3 as an example. This is the expanded equation of 5 plus 3, all from the recursion of addition and Peano axioms. This is just one part which summarizes the 360 pages of proof of the existence of number and the arithmetic behind it. It's unreadable, like not English. Now that's covered, let's talk about 10, 100, 1000. They are unique as an identity, which is proposed in second Peano axioms, or the law of identity by Plato. However, those numbers are not unique because we use multiple unique symbols that represent their value, unlike language that has its own words for all the numbers. 1 and 0, 2025, 3 million. How can we put numbers in their place accordingly? Let's go down to the base. To put it simply, every single digit has n amount of unique numbers. That n is the radix, also known as base. We usually count using 1, 2, 3, and so on, until there are no more unique numbers to substitute the value. Take 15 as an example. From our previous discussion simplified, we slowly add the first digit by 1 until it reaches 10. After 9, we return to the start of the number line and make another counter for the second digit. can imagine the number line as a circle racetrack. For every revolution of the current digit, it raises the next digit by 1. This is the number 15. Technically, all digits which have no value can be written with 0. I'll continue from this 15. But what does it mean by no value? In the first definition of addition recursion, which is written like this: no change has made in the variable a, therefore we can say that 0 has no value. Also, we didn't know how big numbers can get from operations, so for efficiency and simplicity's sake, we can remove all the zeros on the left. What about 100, million? We know how to write 100 by putting 1 in the third digit and 2 zeros on the right. It's quite funny if we also remove the zeros from those numbers, leaving a gap when doing operations. We can go back to the visual representation of how digits work as a racetrack. If the corresponding digit has gone through one or more revolutions of addition, halfway, or even 1, 0 must be in the previous digits as a placeholder of the desirable value. This works for any n base. One of the most popular bases is base 2, also known as binary. We shorten the racetrack to 2 points, which is labeled by 2 unique numbers, 0 and 1. Let's take 11. We don't call this 1011, since the base is different. English orbits around base 10 to count, where every number has its own words. For every number in a different base, we must call every digit in its ones position, 1, 0, 1, 1. After this discussion, we know the labeling of any value in any radices is different. But how do we convert each base to another? Follow for part 2.